exam 2 is scheduled. Exam 2 is open book and open notes. So make sure you bring what you need to bring for exam 2. You'll also need to bring a calculator. So exam 2 will cover all the topics since exam 1. And those topics will include equilibrium and thermodynamics. So I hope all of you are entered into some event in the Physics Olympics today. I can feel the excitement in the air.
What's here? Is it all day? You can tell them. Some of that.
Okay, so we were talking about fuels on Tuesday in lecture. So here's a table which shows the heat and work comparison of various fuels. So note that are any of these fuels, are any of these reactions favored by enthalpy?
Yes.
Well, let me ask this question. Are there any reactions which are not favored by enthalpy? So for a reaction to be favored by enthalpy, is delta H greater than 0 or less than 0? Yeah, so less than 0. So we know that from this column here, all the delta H's are less than 0. Therefore, all these reactions are favored by enthalpy. Are any of these reactions favored by entropy? So I'm missing a few here. I didn't do these calculations for you. Yeah, so are any of these reactions favored by entropy? So for example, is this reaction favored by entropy? What about C4H10 butane? What about C6H14? So for a reaction to be favored by entropy, delta S has to be greater than 0. Which of these reactions do not produce work? Yes, note that this reaction, the combustion methane, does not produce work. Are there any other reactions which do not produce work? Yes, note that when H2 undergoes combustion, that reaction does not produce work. Okay. So I put this slide in because there's a lot of research and there's a lot of money being put into developing ethanol from corn, or actually from corn and various other sources like switchgrass or sugarcane. So anyway, there's quite a few companies which are trying to convert corn to ethanol. For example, Archer's, Daniels, Midland. So we did have a few of these calculations. We know that the combustion of ethanol is an exothermic reaction, and we also did these comparisons. We compared heat and work from ethanol to that of octane, so we can look at this previous slide to figure that out. So if you look at ethanol compared to octane, note that which one produces more heat, ethanol or octane? So I know how much all of you love numbers because you guys are going to be scientists and engineers. So you're going to be spending a lot of your time as professionals working with numbers. And speaking of numbers, did you know that the national debt is what, $13 trillion?
That's a lot.
Did you also know that the average American has an income of about $45,000? And did you know that the average American has a debt of $75,000? So,
That includes their home, their car.
no, these are some numbers. So you guys, you know, these numbers mean something. Yeah, this, I think the U.S. I was reading too is I think the only country in the world which has, which will loan individuals money over a 30-year period. That's that 30-year mortgage. Love it.
So then, do you mean to tell me that it's not likely that I'll be making more than $250,000 in 1 year in my lifetime?
See, it depends if you want to be part of the 1%.
Oh. Do you?
Yeah, so I'm not saying, that's just the average. So if the average income is $45,000 per year for the average American, that means there are people making less than that than people making more than that.
$250,000 would be on the high side.
Yeah, that'd be actually probably in the 2 or 3%. I think the 1% is what, $750,000 or something like that. Okay, so if we compare ethanol to octane, which fuel produces more heat? Yes, know that octane produces more heat on a per gram basis. So no, it's actually almost twice as much. And in terms of work, which one produces more work? Ethanol or octane? Yes, we know that in this table here, both ethanol and octane have a work which is less than 0, but how do we know that octane produces more work? Yeah, looking at delta answers, note that it produces more gas products than, or relative to gas reactants than ethanol does. Okay, so go back to this slide. Okay, so anyway, some scientists believe that ethanol is not the solution. So it turns out that one more statistic is that do you know how much of the corn which is grown is used for food? More than 50% or less than 50%? Yeah, a lot less than 50%. Something like 10%. Okay, so anyway, here's a few articles if you're interested. Now on Tuesday in lab, you figured out the amount of work done by or on food. So this is the chemical equation that represents that reaction. When food burns, we know that when food burns, gases are produced. You figured out how to measure the amount of gas produced. A lot of you measured pressure. Actually, some of you measured the pressure. Some of you tried to inflate a balloon to measure the volume of gas produced. Last week you measured the energy content in food, that's Q. On Tuesday you measured work. So based on Q and W, which are these non-thermodynamic quantities which can be directly measured, you can calculate these thermodynamic quantities which cannot be directly measured. So in other words, based on Q and W, you can measure delta H, delta E, delta S, and delta G. So what you can do to figure out the thermodynamics of burning food is to relate these thermodynamic quantities to these non-thermodynamic ones. So in other words, if we have delta H, how is delta H related to Q and W? So delta H is equal to the Q. How is delta E related to Q and W? So that's equal to what? Q plus W. How is delta S related to Q and W? Yes, this is actually greater than or equal to Q over T. So delta S equals Q divided by T under equilibrium conditions. Under non-equilibrium conditions, all we can say is that delta S is greater than Q over T. And then finally, we can calculate delta G, which represents this balance between the two driving forces, which determines whether a reaction occurs. So delta G is equal to
Delta H minus T.
yeah, so delta H minus Roberto T
Delta S.
delta S. So based on these non-thermodynamic quantities, which can be directly measured, you can relate those to these thermodynamic quantities, which cannot be directly measured. So really, you can calculate delta H, delta E, delta S, and delta G for the food that you burned in lab on Tuesday and last week. Okay, so today what you'll be doing is you'll be making a solar refrigerator. So let's actually talk about refrigerators. So a refrigerator is a heat engine in reverse. So here's the schematic of a heat engine, which we talked about. So if a refrigerator is a heat engine in reverse, use those arrows that to show heat in, heat out, and work from this diagram. Okay, so what do we do with the work? Okay, so is work pointing to the left or to the right? So is it going this way or is it going that way?
That way.
That way. So is it this way or that way?
That way. This way.
To the left.
Okay, it should be going left. Okay, so work. Remember that in a heat engine, work is produced. So in a refrigerator, which works as a heat engine in reverse, we have to supply work to make the refrigerator work. Okay, so what does that work do? So the function of a refrigerator is to take away heat. So where is the heat taken away from? Yeah, so note that the cold reservoir is where heat is being removed. Okay, so your cold reservoir, where is this in our refrigerator? So you're trying to remove heat, and then when you remove heat, what happens to the temperature? Yeah, temperature drops. So you're trying to remove heat so the temperature drops in which part of the refrigerator? Yeah, inside the refrigerator. That's your refrigeration department. So you put work in, heat is removed from the cold reservoir for inside the refrigerator, and what goes in the hot reservoir? Yeah, QH. So let's take a look at the schematic diagram of a refrigerator. So here's 4 There's 4 steps. So in step A low pressure gas is converted to a high pressure gas. In step B, the high pressure gas is converted to a high pressure liquid. In step C, the high pressure liquid goes through a valve and is converted to a low pressure liquid. Then in step D, the low pressure liquid is converted to a low pressure gas. Then the cycle continues again. Okay, so let's write this down. So in step A, let's see, we have a low pressure gas going to a high pressure gas. Then step B, okay, so we said in this diagram that we have to supply work